Dr. Rakhesh.
Yes, yes, I'm here.
Yes, sir. Good
Hi.
afternoon, sir, and welcome.
Thank you.
And sir, thank you very much for accepting our invitation as a resource person, sir.
Yeah, thanks.
Thanks, sir. Yeah, Adit.
Yes, sir. 1 minute is left. Sharp 3 o'clock we will start. Sorry, 2:30. 2:30 we will start.
So, sir, Rakesh, sir, what is the COVID position over there in Guwahati, sir?
Can you hear me?
Yes, yes, yes.
Okay.
So, sir, what is the position over there regarding COVID, sir?
So the COVID, I think in the campus itself, IIT campus itself, we have few cases every day.
Okay. So, you started as a physical mode, sir?
No, no, physical. We are still in online mode. This whole semester would be online mode.
Okay, okay. Good. So, Adit, now you will just start the session.
Okay, sir.
Okay.
Thank you very much.
Okay.
Okay. Good afternoon to one and all present here. I, Aditya Agrawal, welcome to the 4th day and 13th session of Atal FDP on Nanoelectronics and RF Engineering at SRM Institute of Science and Technology. Today we have a distinguished guest, Dr. Rakhesh Singh Kshetrimayum, is with us for this session. Since 2005, Professor Rakhesh Singh Kshetrimayum has been a faculty member with the Department of EEE IIT Guwahati. Presently, sir is working as a professor and was the former head of the Center for Career Development from 2018 to 2020. He did postdoctoral research at the Department of Pennsylvania State University, USA, and the Department of Electrical Communication Engineering, IIT Bangalore, from 2004 to 2005. Professor Rakhesh Singh Kshetrimayum, senior member IEEE, received the PhD degree from the School of Electrical and Electronics Engineering, Nanyang Technological University, Singapore, and BTech degree in Electrical Engineering from the Indian Institute of Technology, Bombay. From 2000 to 2001, he worked as a software engineer with the emphasis Pune. His research interests are in the area of antennas, RF circuit designs, and performance analysis for beyond 5G technology. He has authored and co-authored 4 books and more than 130 papers in international journals and conferences proceedings. Professor Kshetrimayum is an editor of the IEEE Communications Letters and an associate editor of the IEEE Open Journal of Antennas and Propagation. He has also served on the editorial board of the IEEE Transactions on Microwave Theory and Techniques and on the program committees of the several international conferences, including IEEE Global, GlobeCom, IEEE, ICC, and APMC. He is currently serving as an advisor of the IEEE Guwahati subsection. He has received multiple Best Paper Awards, such as IEEE ANTS 2017 Best Paper Award, third prize. He is a fellow of the IET UK. Sir, we welcome you to the forum. We are looking forward for an interactive technical session. The topic of the session is inter-antenna and its effects in Mimo Wireless. Over to you, Professor Dr. Rakesh Kumar Kshetrimayum, sir. Sir, please.
Okay. Thank you, Dr. Aditya. I think I will start presenting the talk.
Yes, please, sir, please.
I hope my screen is visible to everyone. Okay.
So now, yes, sir.
Okay. Thank you. So I will start the talk. The talk is about inter-antenna interaction and its effect in Mimo Wireless. And before the starting of the talk, I want to acknowledge my students. This is okay. This is Mr. Mohit Misra. He's in the final stage of his PhD thesis. And this is Dr. Sumatra Chaudhary. He recently defended his PhD thesis. And this is Dr. Anirban Powell. He's a postdoctoral fellow at INRSCMT Montreal, Canada. And this is Dr. Bidesh Kumbani. He's an assistant professor at IIT Roper. So these four students, they have a significant contribution in this talk I'm going to give today. So the outline of this talk would be divided into three sections. The first section I'll discuss about what is Mimo Wireless, what are the fundamental gains of Mimo Wireless. So I'll call this as wireless perspective. So we need to have a little bit background on the wireless in order to understand the Mimo antenna. Then we'll move on to inter-antenna interference parameters from the antenna perspective. I'll define what are the fundamental parameters for Mimo antennas. Then in the third section and final section, I'll discuss about the Mimo antenna performance metrics. What is the most appropriate way of defining the Mimo antenna performance metrics? Okay, so in section 1, we'll discuss about what are the fundamental gains we have from Mimo antenna. One is called diversity gain, another is called rate gain. So the question is, can I increase this diversity and rate gain of the Mimo system simultaneously? So it's not possible. Actually, there is a trade-off, which is the famous multiplexing diversity trade-off. We'll discuss about that briefly. Then we'll define what is inter-antenna interaction parameter in terms of wireless perspective. Then finally overcome that by applying some technique called spatial modulation, which actually remove the inter-antenna interference completely. Then we'll go to the antenna perspective. So in the antenna perspective, we'll discuss about the inter-antenna interaction parameters, such as some people who are working in the Mimo antenna area, they must be knowing what is mutual coupling. So we'll discuss mutual coupling, what are techniques to reduce mutual couplings. Then we'll move on to envelope correlation coefficient, and we'll also define what is the relation between the envelope correlation coefficient and the mutual coupling. And the mutual coupling basically can be calculated in two ways. One is from the radiation pattern, and another is from the scattering parameters. So whatever, so envelope correlation coefficient can be calculated from the 3D radiation patterns or from the S parameters. So the ECC calculation from the S parameter is very easy to calculate. Once you have the scattering parameters, you can just plug in and find the ECC. It's quite easy, but it's actually applicable only for highly efficient antennas. So some popular antennas like microwave antenna, you cannot use ECC calculation from the scattering parameters. You have to use 3D radiation patterns. So this is a more accurate way of calculating the ECC. So once we have the ECC of the Mimo antenna, we can actually calculate what is called antenna correlation coefficient. So this is the most fundamental parameter. Once we have this antenna correlation coefficient, then we can actually characterize the performance of Mimo antennas. So once we have the antenna correlation coefficient matrix, we'll actually find out what are the performance metrics of Mimo antenna for different kind of Mimo systems. So Mimo actually started somewhere in 1994, and that was called single user Mimo. Then in around 2007, we have something called multi-user Mimo, which has a better performance. Then similarly, we have more and more better performance Mimo system like massive Mimo, which is very popular. It's already used in 5G wireless communication system at the base station and for the mobile users. Then somewhere in 2017, people has proposed something called cell-free massive Mimo, where we don't have any kind of cells, hexagonal cells we have been assuming in the cellular communication for many years. So Mimo is evolving from 1994 till today. So the performance metrics for antennas which are employed in the Mimo system is also changing. So performance metrics for Mimo antenna for single user Mimo we'll discuss first, then we'll move on to multi-user Mimo. So when we move from one Mimo system to another Mimo system, the performance metrics change. So that we'll have a discussion on that. After that, we'll move on to massive Mimo and cell-free massive Mimo. But in the antenna community, the characterization of Mimo antennas in the massive Mimo and cell-free massive Mimo is not done properly. So this is an open problem. But anyway, we'll discuss about the effect of spatial correlation on the massive Mimo and cell-free massive Mimo. Then finally, I'll conclude the talk. So any wireless communication cannot happen without antennas. Antennas are everywhere. So I'll just show some typical antennas. These are typical base station antennas we see now and then. And this is one full duplex antenna we have designed and fabricated in our lab. And this is a DRA area. We have dielectric blocks here, 6 of them. We have designed this for anti-vehicular anti-collision vehicular radar applications. So these are the papers where you can explore about this antenna. So antennas are everywhere. Everywhere we go out, we always see antennas. So wireless communication is impossible without antennas. So antenna is a very important part of the wireless communication. Similarly, here also in MIMO wireless communication, we'll first start from the traditional wireless communication. In traditional wireless communication, what we have is single input, single output system. So we have a transmitter, we have a receiver. Transmitter is fitted with a transmitting antenna, receiver is fitted with a receiving antenna. So let us look at the channel. Channel is the medium in which we are doing the communication. Looking at this channel, we have input from one transmitting antenna. It is giving output to one receiving antenna of the receiver. So that is single input, single output system. So this is the traditional wireless communication system. But as I have told you, somewhere in 1990s, MIMO wireless has come into picture. What is this MIMO wireless? So let us define this MIMO wireless. So here we have a transmitter. Transmitter has NT number of transmitting antenna and receiver has NR number of receiving antenna. So if you look at the channel perspective, so how many inputs we have from the channel? Channel has NT inputs from the NT transmitting antennas of the transmitter. Channel has output to the NR antennas of the receiver. So we have multiple input, multiple output system. So that's why we call MIMO system or multiple input, multiple output system. So what do we want in any wireless communication? So what are the performance metrics for any wireless communication? Obviously, we want a higher data transfer rate. That's the first thing. Second is we want less error in data transmission. So any wireless communication, we want higher data transfer rate and less error in data transmission. So in terms of that, how do we characterize the performance of any wireless communication system? So if anyone is working in performance analysis of wireless communication system, we actually consider only three criteria for any wireless communication system. So these are all wireless examples. For all these wireless communication examples, the three criteria is first is channel capacity. So what is channel capacity? That's a maximum data rate one can transfer over the channel with minimum probability of error. So maximum data rate one can transfer over the channel is called the channel capacity. And we also need to minimize the probability of error. That is the error in data transmission. So as soon as we are transmitting at the data rate which is greater than the channel capacity, then at the receiver won't be able to decode the message which has been transmitted from the transmitters. We'll have a lot of errors. So that situation is called outage. So when we talk on mobile phone, sometimes we cannot hear anything from the other side. No? Those kind of things are called outage. So outage is whenever you're transmitting at a data rate which is greater than the channel capacity, there will be a lot of errors at the receiver. Receiver won't be able to decode the message. So we are in outage. The probability of that is called outage probability. Then the most fundamental parameter is the probability of error in data transmission. This is actually the bit error rate or symbol error rate or packet error rate. So this is basically that. Okay, so that's about the MIMO wireless and performance characterization of any wireless communication system. So let us try to understand why people are so crazy about this MIMO wireless. Basically, people are very crazy about the MIMO wireless is because we have two fundamental gains in the MIMO wireless. First gain is called the rate gain. We'll maximize the rate. If we have higher and higher data rate in transmission, we have a better wireless communication system. So that is called the rate gain. So how much is the rate gain of MIMO wireless with respect to that of the Sysol system? So let us consider one simple example. This is a simple example we have here. We have three transmitting antenna and three receiving antennas. So this is a transmitter fitted with three antennas and this receiver fitted with three antennas. So if I want to transmit 001 from the transmitter, what I can do is I can transmit 1, 0, and 0 from first antenna, second antenna, and third antenna. So over a one-time interval, I'm transmitting 3 bits at a time. But let's look at the Sysol system. So we have a Sysol system. We have one single antenna here at the transmitter and receiver. So if I want to transmit these 3 bits, what do? I first transmit 0. I first transmit 1, then I transmit 0, and I transmit 0. So I need 3 time intervals to transmit 3 bits. So in a way, we are having rate gain of 3 over that of the Sysol system. We are having faster communication, higher data rate transmission. So this is called a rate gain. It is also called as multiplexing gain in the literature. So this is one fundamental gain. We can also analyze this from the capacity of the MIMO channel. So capacity of the IID MIMO channel. IID is independent and identically distributed. Here, we assume that all the transmitting antennas are very far away. All the receiving antennas are very far away. There is no interaction. All of them are independent. We can have parallel transmission. In that case, first thing is that at the transmitter we have n number of antennas. How much power is antenna is going to get can be calculated from the from the power allocation. There are many techniques for power allocation. Simplest one is equal power allocation. You divide the total power by the total number of antennas and give every antenna same power. That is called equal power allocation. So equal power allocation, this is the simplest power allocation algorithm. The capacity of MIMO system is m times that of the Sysol system. So if you have capacity for the Sysol system is C Sysol, then the capacity for the MIMO system is m times the Sysol system. M is the minimum of number of transmitting antennas or number of receiving antennas. If we have more and more number of antennas at transmitter and receiver, we'll have more and more capacity. More and more capacity means we have higher and higher data transmission rate. So let's look at this is the capacity for the Sysol system. If anyone is working in wireless communication, they know this. This is Shannon's formula. So if I want to increase the capacity for the Sysol system, traditional wireless communication system, in that case, I need to increase the bandwidth or I need to increase the SNR. Bandwidth or the SNR. SNR is the signal power. I need to either increase the signal power or I need to increase the bandwidth. But for the MIMO system, whatever capacity gain I have told you, m times that of the Sysol system is without increasing the power and bandwidth. So we cannot keep on increasing the power. There are a lot of interference issue, and we cannot also keep on increasing the bandwidth because bandwidth is very precious. So whatever gain we are getting for the MIMO system, m times that of the Sysol system is without increasing power and bandwidth. So this is a major advantage of MIMO system. We are not increasing the power, we are not increasing the bandwidth, we are having a higher data rate. So for example, if you consider large scale MIMO system, which is projected for 5G and 6G applications, if you assume that m is 100, then capacity will be 100 times of the Sysol system. Or let's say if you have m is 1000, then capacity will be 1000 times of the Sysol system. So the data rate will increase 100 times, 1000 times if we employ MIMO system. So that's one major gain of MIMO system. And another one is the diversity gain. So what is this diversity gain? So let's consider the same setup where we have 3 antennas at the transmitter and 3 antennas at the receiver. So now, in this case, I assume that I just want to send 0 bits, and I assume that 0 bit is sent from antenna 1, 2, and 3. We're sending the same bits from antenna 1, 2, and 3. So this 0 bit can reach the receiver through diverse parts. So if you count the number of parts here, it's a 3x3 MIMO system. 0 bits can be received at the receiver from the transmitter from 9 different parts. So what happens if one or two of the part is down, block, or there is some disturbance? We don't need to worry. We get the 0 bit from the other remaining parts. So we can easily decode the message. But let us consider the traditional wireless communication, which is a Sysol system. We just have one transmitting antenna. So one transmitting antenna, then we just have one path for the signal to reach from the transmitter to the receiver. So if this link is down, then if we send 0 from here, receiver won't be able to decode the message. It will get a lot of errors. So basically, when you consider that diversity gain is there, it's a number of diverse parts the signal can reach from the transmitter to the receiver, will have a decrement in the probability of error, or will minimize the error rate in the data transmission. So we want 2 things. One is higher data transfer rate, another is a minimum error. So both of the things are achieved by the MIMO system. So so I want to spend a little bit on the probability of error calculation, and those who are working in the wireless communication, they know already, but those who are not working in that area. So probability of error can be simply calculated. When you do simulation, you send some fixed number of bits, and how much bits are in error at the receiver, you just divide those two, you get the bit error rate. So bit error rate is actually your probability of error. So number of bits in error divided by the total number of bits. And for example, if you are sending 5 bits, simple examples, especially for those who are not working in this area. So if you are sending 5 bits and these 2 bits are in error, these red colored bits are in error, in that case, how much is the bit error rate? It's 2 by 5.4. This is called probability of error in the wireless communication also. SNR is the ratio of the signal power divided by the noise power. If we increase the SNR, if we keep on increase the signal power, then there will be less error in the data transmission. So this graph actually shows what is the difference between the Sysol system and the MIMO system. If you look at this graph, we have here is the probability of error versus SNR curve. So if you keep on increasing the SNR proto error will be minimized. So we have three graphs here, one for the uncoded system. Uncoded system or the usual Sysol system, the graph will be almost like a straight line here. But if you have a MIMO system, the graph will have higher slope. So this is for the simple Sysol system. This is for the MIMO system. We have a higher slope. Because of that, there is a lot of gain. We'll discuss that in the following slides. So what is the advantage of having higher slope? What a higher slope in the proto error versus SNR curve? This can be simply understood from this discussion we have in this slide here. You consider the simple case, Sysol case. If you find a proto error versus SNR, SNR is the signal to noise ratio. The relation would be proto error would be 1 by SNR. So that will be a straight line, obviously. And the proto error versus SNR curve for a MIMO system is 1 by SNR to the power diversity gain. So how much diversity gain you have, because of that slope is going to keep on increasing. So this is a typical curve for the Sysol system, and this is a typical curve for the MIMO system. We see that there is increase in the slope here. Because of that, what is the advantage? We'll discuss that now. First thing is that if you first fix the SNR, we are fixing the signal power. We're fixing the signal power, SNR is 20 dB. Let us look at the how much is the proto error. Proto error for the Sysol system is 0.5 into 10 to the power minus 2. But if you consider for the MIMO system, proto error is 0.5 into 10 to the power minus 5. So for the same power of signal we are using for sending the signals, if you use MIMO system, the proto error is minimized significantly. This is one advantage, first advantage of that. Second one is, if you consider a fixed proto error, we fix the proto error is 10 to the power minus 4. How much signal power we require? For the Sysol system is around 27 dB, but for the MIMO system is 17 dB. There is a significant reduction in the signal power we need to send over the channel to have the same proto error. So MIMO is an energy efficient communication. People are using it for green communication also. So that's a major advantage of the diversity gain. So the question is, can I keep on increasing this diversity gain and rate gain simultaneously? If that's possible, that's the best situation, but that's not possible. Actually, there's a famous trade-off called diversity multiplication trade-off. These are actually calculated by some people from MIT. They have come up with this relation. What they say is, if you increase the rate, R is the rate gain, then diversity gain will decrease. So there's a trade-off. You cannot keep on increasing rate gain, and you cannot simultaneously get higher diversity gain. So there's a trade-off. So all the MIMO wireless communication has to be designed using this trade-off. So let us look at the simple example. If you have a 5 by 5 MIMO system here, that means 5 antennas as a transmitter and 5 antennas as a receiver. In that case, what I need to do is I need to use some of the antennas for the rate gain and some of the antennas for the diversity gain. So let's look at it. For example, if I use 3 antennas for the rate gain, then the remaining 2 antennas I can use for the diversity gain. So in this case, I will get rate gain of 3 and diversity gain of 4. So you have to design your MIMO system based on this diversity multiplication trade-off. Okay, so let us look at the simple input-output system model for the Sysol system. So we have input is the signal we are transmitting from the. So basically, we need to look at the channel. No? Channel is having input from the transmitter. Let's say we are sending symbol X. That's the input to the channel. And what is the channel? Channel is the H. If we denote the channel by H, what are we receiving at the receiver? We are receiving Y is equal to X plus N. So channel is multiplicative. You just multiply the channel with the input signal, then you get the received signal at the receiver. And you don't need to forget this term here. This is a noise which is obtained at this receiver. So this is called AWG noise. This is a simple model for the single input, single output system, traditional wireless communication system. But as soon as you go to the MIMO system, there is a slight change here. See, for example, signal you are sending from this transmitting antenna 1 can reach to receiver 1 and receiver 2. And signal you send from the transmitting antenna 2 can be received by receiver 1 and receiver 2. And the paths, we have 4 different paths here. So you have to write Y1 is a signal received by this antenna 1 is X11, X1. So this is one path, X11 into X1. Another one is X1 to X2. This is a signal which is coming to this here. So these are the 2 paths, 2 signals which are coming from the transmitter. And you need to add the noise again. Similarly, you have to do it for this. This should be Y2. Y2 is H21, X1 plus H22, X2 plus N2. But there's a simple way of taking into account of MIMO system. You just convert everything to matrix. So if you are very good and expert in matrix, then MIMO is no longer a difficult subject for you. Everything should be converted into matrix. So the Y vector, Y would be a vector because we have Y1 and Y2 which is received at the receiver. Noise will again be a vector N1, N2, and channel will have H11, H12, H21, H22, and signal we are transmitting X1 and X2. So you can write in a very compact form Y is equal to Hx plus N, where Y is a vector, X is a vector, N is a vector, H is a channel matrix. So everything you have for the Sysol system, when you go to the MIMO system, it will become matrix and vector. So that only changes. System model still remains the same. So if you want to explore about the Mimo Wireless, I have one book on fundamentals of Mimo Wireless published by Cambridge University Press. This is another book I have written with Vijay Kumbani. This is Mimo Wireless Communication over Generalized Fairing Channel published by CRC Press USA. Okay, so we have the input-output system model for the MIMO system. That was for the 2x2 MIMO system. As I have already told you, if you want to go to the MIMO system, you have to convert everything to vectors and matrix. If you have NT by NR MIMO system, the received signal would be Y1, Y2, YNR because we have NR antennas. And channel matrix will be NR by NT matrix. Then signal we are transmitting, we have just NT antennas. So X1, X2 up to XNT is the signal transmitted from antenna 1 to antenna NT. So it will be just matrix from Y is equal to Hx plus N. Now, what is inter-antenna interference in the MIMO wireless? So we have Y is equal to Hx plus N. Look at this term here. The received signal for antenna 1, R1, is a combination of the symbols which has been transmitted from the antenna 1 and antenna 2 of the transmitter. So we have basically mixture of signals at the receiver. So it's very difficult for the receiver to detect the symbols which has been transmitted from the transmitter because of this interference between the symbols. So what is the receiver duty is to decode the symbols which has been transmitted from the transmitter. So this is the estimate of the symbols. It can be done by using this Euclidean distance estimation here. Minimize the Euclidean distance between the received symbol vector with the transmitted symbol vector. You find out the Euclidean distance between the received symbol vector and with all possible transmitted symbol vectors, which one give you the minimum one, that would be the symbol which has been transmitted from the transmitter. So when receiver does this, so in wireless communication, receiver is the most difficult part. So transmitter side, everything is not that difficult, but receiver is the most difficult part. And receiver has to do a lot of comparison. So let us just try to see how many comparisons receiver has to do it. That comparison can be expressed as m to power nt. M is the symbol alphabet size. For example, if you consider 4QAM, 4QAM will have 4 symbols, 0001, 1011. So in that case, m 4 to the power nt. So if you keep on increase the number of transmitting antenna, this number of metric comparison you do at the receiver is going to increase. That's a simple calculation we have here. So let's look at it. For example, if you consider 4QAM, which is the most widely used modulation schemes in the literature, if you have a 2x2 MIMO system, the number of comparisons receiver has to do will be 16. And if it is 4x4, then it's 64. If it is 5x5 MIMO system, that means 5 antennas at the transmitter and 5 antennas at the receiver. The number of comparison is 1024. But let's say if you consider large scale MIMO, 100 by 100 MIMO system, the number of comparisons will 10,48,576. So this is a real headache for the receiver. So receiver want to get rid of this. So this is the inter-antenna interference at the receiver side. We want to get rid of this. Is there any technique to do that? So we'll discuss that. There are some techniques in the literature. We have been working in this area, spatial modulation. So in the spatial modulation, what do? We actually have NT antennas at the transmitter, NR antennas at the receiver, but don't use all these antennas. Just use one single antenna and transmit symbol from there. Let all other remaining antennas sitting idle. So even with that, we have very good performance in the MIMO wireless communication system. This is called spatial modulation. You do modulation over space. This antenna index will also carry some message width. So we'll see that one simple example in the next slide. So the idea is just make one antenna active. So in that case, receiver will receive symbol from only one antenna. There is no inter-antenna interference. Only one symbol will be received by all the receiving antenna. So that's a basic idea. So we can take one simple example. Let's say if you have a 2x2 MIMO system, I have 2 transmitting antenna, 2 receiving antenna, and we use 4QAM modulation system. In that case, we use this mapping table, and in the mapping table, the first bit will decide which antenna to be active. So if you have zeros, in the incoming bits, if you have zeros, you'll transmit from the antenna 1. If it is 1, you transmit from the second antenna. So if 0 then transmit from the first antenna, you have a switch here, RF switch, so we need the RF switch here. So from here, from the transmitter, you connect to this antenna using RF switch and connect to this antenna 1 if your first bit is 0. If your first bit is 1, you transmit from the second antenna, you connect this RF switch to this second antenna. And the remaining 2 bits will decide which symbol to be transmitted from this antenna or this antenna. That's a simple technique. And at the receiver, you have to estimate the index of the antenna which has been transmitted from the transmitter as well as the symbol which has been transmitted. Both of them will carry message bits. And let's take simple example. If the incoming bit is 011, 011, then 0, so we need to connect this switch to the first antenna, and 11 means we'll transmit the symbol -1 plus j. At the receiver, both the antennas will receive only one symbol, which is -1 plus j. So it will estimate this symbol. It will get this symbol after estimation -1 plus j. It will also find which antenna has been used for transmitting the symbol. If it finds out that first antenna is used, it will decode 0 bit. If it is second antenna is used, it will decode 1 bit. So this is the process. So this is a very efficient technique. You just make one antenna active, all other antennas are sitting idle. There is no inter-antenna interaction or interference at the receiver side. Okay. I think I will skip this. Okay. We are discussing a lot of things about the wireless communication. So if you want to explore about the spatial modulation, you can refer to our book. It's a recent book published by Sprenger in 2021 with Dr. Anivan Ball. Okay, so what we have seen is that in wireless communication also, we have some techniques to reduce the inter-antenna interaction. So let us come to the core of our today's talk about the MIMO antenna. So just before going into MIMO antennas, let us try to see what is inter-antenna interaction in a MIMO wireless or an antenna array. So this simple diagram will actually give you what is inter-antenna interaction. So let's say if I have antenna 1. So antenna 1 is located somewhere in free space. It's a standalone antenna. It is radiating signals like this. This is the radiation pattern. So would there be any kind of inter-antenna interaction or inter-antenna interference? No, there won't be any kind of inter-antenna interaction or interference because this is a standalone antenna. Let's say we bring in another antenna. And this antenna is also having radiation pattern like this. So all antenna engineers know that this antenna 1 and antenna 2 will not have any kind of interaction because radiation patterns are directed in a different in the same direction and they are very far away. So since these two antennas are very far away, there won't be any kind of inter-antenna interaction. So the first criteria for inter-antenna interaction is the inter-element distance. Closer and closer antennas will have more and more interaction. Second criteria, the second criteria is the orientation. Let's say I bring in another antenna in between these two antennas and orient this antenna. This is a symbol for the antenna. This is a symbol for the radiation pattern. If I orient this antenna in this vertical direction, this antenna 3 and antenna 1 will have a lot of interaction. So antenna orientation is the second parameter. So if we orient antenna properly, we can minimize the inter-antenna interaction. Another thing is the radiation pattern. So this antenna 3 and antenna 2 won't have any kind of interaction because beams are directed like this. But let's say this antenna has a back lobe. It has a back lobe, then it will start radiating signal in this direction. There will be a lot of interaction. So the three most important parameters for inter-antenna interaction is inter-element distance, orientation, and radiation pattern. Okay, so what will happen when we have this kind of situation in the MIMO wireless? Let us try to understand the same thing by considering the 3x3 MIMO system for red gap. We have 3 antennas at the transmitter, 3 antennas at the receiver, and we want all the antennas to transmit signal independently. And if all antennas are having radiation pattern like this and they are sufficiently far apart, there won't be much interaction between antenna 1, 2, and 3. So there is no inter-antenna interaction. But let's say, and let's consider another situation. Same situation, but let's say this antenna radiation patterns for antenna 1, 2, and 3 are having side lobes. In practical situation, many of the antenna has side lobes. So now you can see that signal can go here, there will be a lot of inter-antenna interaction. So this is another situation where you have a lot of inter-antenna interaction. And let's say side lobe is, you design your antenna properly, so we don't have any kind of side lobes. But then also, if you place your antenna very closely, radiation pattern will start overlapping. There will be a lot of inter-antenna interaction. So antenna engineers has a definite role, very good role in the MIMO wireless communication system. And one of the major thing is we need to design our antenna so that we can minimize the antenna interaction. We'll discuss many examples, typical examples later on. Okay, similar situation if you have, for the case when you have a diversity gain also, you need to have a diverse path here. If the paths signals has gone from one antenna to another antenna, if they are overlapping, there will be a lot of inter-antenna interaction. Okay, so let us come to the parameters which antenna engineers use to define for MIMO antennas, inter-antenna interaction parameters. The first is the mutual coupling, and I will discuss all this in brief later on. And typical value of mutual coupling should be less than minus 15 dB, and we find that if you design your antenna, MIMO antenna, and mutual coupling is less than minus 15 dB, so it's acceptable in the literature and in the antenna community. So mutual coupling should be less than minus 15 dB. Then another thing is the envelope correlation coefficient. Envelope correlation acceptable value is 0.5, but I have seen that nowadays people are always going for less than 0.1. So envelope correlation coefficient is a very important parameter. We need to minimize it. 0.5 is the acceptable value which is reported in the books, but nowadays everyone is going for higher and higher, lower and lower value of the envelope correlation coefficient. People are going for 0.1, 0.01. I will show you some antenna design where we have envelope correlation coefficient less than 0.1. Another thing is the antenna correlation coefficient, and they are actually related. Once you have envelope correlation coefficient, you can take square root of the envelope correlation coefficient, you can get antenna correlation coefficient. So if you have acceptable value of envelope correlation coefficient is 0.5, then acceptable value of ACC is 0.7. Square root of 0.5 is around 0.7. So these are the acceptable values of the antenna interaction parameters. We'll spend in details. Okay, so first thing is the mutual coupling. Just before that, let us try to understand what is the difference between the MIMO antenna and traditional antenna. Traditional antenna, this is a typical this microwave antenna we use in our lab for microwave antenna measurements. And this is a microwave antenna, and all the antenna engineers know it. Let us look at this antenna. How many ports it has, how many elements it has. It has one radiator, it has one input port. So it's a one port, one element device. But look at the MIMO antennas nowadays. This some of the antennas we have designed in our lab, fabricated and tested in our lab. Look at this antenna. We have two radiating elements, two ports. And similar, this also two radiating elements and two ports. So MIMO antennas are multiple ports, multi-element antenna array. So it's different from the traditional antenna. Traditional antenna has single port and single radiating element. MIMO antenna has many radiating elements, many ports. So we call this MIMO antenna as multi-port, multi-element antenna array. And the performance characterization for MIMO antenna is going to be definitely different from the traditional antenna, which has one single port and one radiating element. Okay, so let's discuss about the mutual coupling. How do I measure this mutual coupling in the lab? So this is the network analyzer. Everyone knows what is a network analyzer. It will measure the scattering parameters. And it has two ports, port 1 and port 2. And let's say if I want to measure the mutual coupling, what should I do? We have coaxial cables which are used as wire at high frequency. All the connectors are connected using the coaxial cables. So I connect this port 1 with the port 1 of the MIMO antenna using this coaxial cable, and port 2 with the port 2 of the network analyzer with the port 2 of the MIMO antenna. So then I send some signal from port 1. How much signal is picked up by this port 2? That is the mutual coupling. We call this as S12 parameter. This for a 2x2 MIMO, two element MIMO system, we can measure mutual coupling like this. But let's say if you consider this is the anechoic chamber. Everybody knows, all antenna engineers knows. It's a quiet chamber where we do all the antenna measurements. This is the quiet chamber we have at IIT Guwahati. This is transmitter, this is the receiver, this is antenna under test. So we want to measure the mutual coupling for, let's say, 6-port, 6-element MIMO antenna. This is one of the antenna we have designed. It's a highly compact MIMO antenna array. We have 6 ports here. We also have 6 elements here. So then how do I measure mutual coupling? Network analyzer has only 2 ports, right? So how do I do that? Let's say I want to measure S16, mutual coupling between port 1 and port 6, or element 1 and element 6. So similar kind of situation, I connect port 1 with the port 1 of the MIMO antenna, port 2 with the port 6 of the MIMO antenna. Then I cannot keep all this remaining port open. There will be a lot of reflection. I won't be able to do any kind of measurement. So what I need to do is, in order to minimize the reflection, I put a mat slot everywhere, mat slot connection. Then I measure it. Signal I transmit from port 1, how much signal is received by port 2, that's S16. Similarly, you can measure all the scattering mutual coupling parameters. Okay. From the scattering parameters, we can actually calculate the envelope correlation coefficient. Envelope correlation coefficient, this is a formula for calculating envelope correlation coefficient between element I and J. We have scattering parameters here. So I want to see this formula is there in the literature, but I want to dissect this formula. If anyone wants to work in the MIMO antenna area, they need to know how this formula has come up. You need to know fully what is this formula instead of just remembering the formula. We need to know what's going on. So I actually want to expand this numerator term here. So I can expand it like this: multiplication of this with complex conjugate of this. Then I can separate this as first term and this as second term, and I want to understand what is the first term and this second term here. Okay, so let's look at the denominator of the first term. So denominator of the first term is this: 1 minus SII square plus XIJ square. What is this? Let's say signal is coming from port 1. Port I. Signal is coming from port I. How much is reflected? That is your SII. How much is transmitted is your SJI. So this term is that. So let's say incident signal is 1, amplitude of the incident signal is 1. How much is reflected? How much is transmitted? You subtract those two. That is the signal power which has remained at this port I. Similarly, you look at the term here, this numerator term here, this numerator term here. Okay, so we know that from the wave analysis, let's say if I consider the wave which is propagating along the x-axis, I will have a term like exponential minus jkx. K is the propagation vector, x is the direction. So this is a wave propagating along the x-axis. If I take complex conjugate of that, I get exponential plus jkx, and this is a wave propagating in the opposite direction, in the negative x direction. So that is required because we have x, SII star, SJI star. So I want to use that here. So let us look at this part here. So this SII is directed. This is a reflected wave at the port I. So it will be directed along this direction. This transmitted wave along this direction. It will be directed along this direction. So what I want to calculate is I am moving like this. So this wave should be in this direction, but this is directed along this. That's why I have a SII star here. This is okay. And how about this one? Again, you look from here. This is the reflected wave at port J. So it will be along this direction. This is the transmitted wave from this to this. So what is the direction? I want to move along this direction, but this is along this direction. I will have a star here. So SJI star here. And this is along the same direction. So this is the first term here. So the wave is moved from port I to port J will compose of two parts, this part and this part. All these parts are sum up here. This is the wave which has remained at the port J, port I. This is the wave which has gone from the port I to port J, port I to port J. Similarly, second term also you can look. Similarly, you can look at the second term. From here, signal which has been refracted is SJJ, signal which has been transmitted is this. So what is remain at this port is 1 minus Sj square plus 1 plus Sij square. So this is the term you have in the denominator of the second term. Similarly, you can also look at signal which has gone from the port J to port I. You follow this part. This is in opposite direction, Sjj star, Sji. Similarly, you consider the other part. This is in the opposite direction, Sij star, Sii. So this is the term you have here in the numerator. This is how you calculate the envelope correlation coefficient. So we have dissected the formula, we understood it. But this formula, as I have told you at the beginning of the lecture, this formula you cannot use every time. This is applicable only for the highly efficient antenna, let's say antenna which is having efficiency greater than 90%. And one more thing you can observe is that Sij and Sji are the mutual coupling terms, cross coupling terms. So those terms are there in the numerator. If we increase the mutual coupling in our antenna design, ECC is going to increase. So if you want to minimize ECC for the antennas, you need to minimize mutual coupling between the antenna elements. This can be clearly seen from here. Another thing is that you have a term here, Sji, Sij here. These are mutual coupling terms, cross coupling terms. So this is one minus of that. So if I increase the mutual coupling, then this term is going to decrease. Overall, ECC is going to increase. So the basic idea is, if you want to minimize the ECC of a MIMO antenna, which is a very important parameter, you need to, so if you want to decrease the ECC of a MIMO antenna, so we want lesser and lesser level of the ECC. In that case, we need to minimize the mutual coupling. So this is a design technique. Minimize the mutual coupling, it will automatically decrease the ECC, and lower ECC is always better. We'll see it later on. So that was the ECC calculation from the scattering parameter, which was quite easy. Once you have the scattering parameter, you can just plug in the formula and you can find out. But that is applicable only for highly efficient antenna. But if you consider ECC calculation from the radiation pattern, then this is much more accurate. Anyway, what we want to do is minimize the inter-antenna interaction. We have seen that radiation pattern was the main factor which will actually minimize the inter-antenna interaction. That is actually taken into calculation of ECC, envelope correlation coefficient, in this ECC calculation from the radiation pattern. You can see that in the ECC calculation here, you have ECC 3D radiation pattern for the IN antenna, Z antenna. So ECC is dependent on the radiation pattern of the antenna, 3D radiation pattern on the antenna, and this is much more accurate because ultimately signal will go from the radiation pattern of the antenna, depending on what kind of radiation pattern you have, directive, omnidirectional, all kind of radiation patterns. Based on that, signal will go. So interaction will be dependent on the radiation pattern. So the ECC calculation from the radiation pattern is much more accurate than calculating it from the scattering parameter, which are actually calculated from the ports. No? So here is from the radiation pattern of the antenna. The scattering parameters we have calculated was between the ports. So that's not a very good way of calculating ECC. So again, I want to know this formula. So I simplify this here. This can be written in this form here. Complex conjugate with itself, you multiply, you get square of that. You have this term here. You can separate this term and this term. You have two terms here. First term and second term. So let us try to understand the formula. We will not just remember the formula. We need to understand the formula so that we gain confidence in our research work. So look at this first term here. In this first term, you have EI, EJ. This is a cross correlation of the I and J fields. It's called a cross similarity of the I and J fields. I element and J element, antenna element fields. This is a cross correlation. Denominator is the autocorrelation of the ith element. Here again, you look at it. This is a cross correlation of the I and J fields, and this is autocorrelation of Z fields. So that's how you find how similar is one antenna element radiation pattern to the another antenna element radiation pattern. From there, you find out what is the envelope correlation coefficient. And once you have the envelope correlation coefficient, from the definition itself, you can take the square root of envelope correlation coefficient, you can get the antenna correlation coefficient. That's the simplest way of finding the antenna correlation coefficient. We find the envelope correlation coefficient from the 3D radiation pattern, which is very accurate. Take the square root of that, you get the antenna correlation coefficient. So antenna correlation coefficient is the most fundamental parameter. Once you have that, you can actually characterize the performance of MIMO antenna. So this antenna correlation coefficient also can be calculated from the scattering parameters. So A and B are the incident and reflected waves. So anyone who has microwave engineering background, we always discuss this in terms of scattering parameters. So A is the incident wave, B is the reflected wave. So if I want to find power radiated, this is the incident power, this is the reflected power. If I subtract the incident power minus the reflected power, I get the radiated power. And I know that reflected wave is equal to scattering parameter into incident wave. So I just substitute that. Then finally what I get is power radiated is A Hermitian, I minus S Hermitian, S minus A. So this portion here is called the antenna correlation coefficient. I minus S summation S. So from here, once I have the scattering parameters, this is the identity matrix. I can find out antenna correlation coefficient matrix. So this is another way of finding the antenna correlation coefficient matrix. If you have a two-element, two-port MIMO antenna, the antenna correlation coefficient matrix in terms of scattering parameter is like this. This is uh, reported in the literature, but one question is that many of the people design MIMO antennas of 3 or more antenna elements, and they still use this formula for 2x2 MIMO system. That's not correct. Let's say if you consider 6x6 MIMO system, this antenna correlation matrix will have 6x6, 36 components, and you have to find out each one of them by using this formula here. This is a matrix. What I have is I minus S summation S. I know scattering parameter, I know identity matrix, I can find out. So let's say O22 is the antenna correlation coefficient between antenna 2 and antenna 2 is this. Antenna 1 and antenna 5 is this. So like that you can find out. This very convenient way of finding the antenna correlation coefficient. But then again, same situation here, we assume that antenna is a lossless device here, but most of the antennas has some inherent losses. We cannot use it for accurate calculation. This is for rough calculation. If you want to do accurate calculation, first calculate envelope correlation coefficient from the 3D radiation pattern, and you find out the antenna correlation coefficient by taking square root of it. So what is the next thing? So let's say you have designed, fabricated, and tested a MIMO antenna. How do you characterize the performance of this MIMO antenna? So MIMO antenna is a part of a MIMO system. You cannot separate it out. No? So MIMO antenna is a part of MIMO system. So the antenna performance matrix you have for the MIMO antenna should be in line with the MIMO system. So if you define any kind of arbitrary antenna performance matrix for MIMO antenna, we won't be able to use it for any useful purpose. So let's say antenna engineers define many types of MIMO antenna performance matrix, but it is not in line with MIMO's wireless communication system. It is useless. So we'll try to define some MIMO antenna performance matrix in line with the MIMO system, which should be really useful for the MIMO wireless communication. So that's the section 3. So let's start with the point-to-point MIMO system, single user MIMO system, only one user. Or let's say you have a transmitter and receiver, you have a transmitting terminal and receiving terminal. So they are communicating. So now let's consider 4 antennas are there at the transmitter, 4 antennas are receiver, or any number of antennas at transmitter, any number of antennas at receiver. This diagram shows only 4 antennas at transmitter and 4 antennas at receiver. So depending on what kind of antenna arrangement you have at transmitter and receiver, the antenna correlation coefficient is going to change. You can arrange this antenna with equidistance. If you have equidistant antenna array, then you will have different correlation matrix. If you arrange this in a circle, like circular array or linear array, the antenna correlation coefficient and the inter-antenna interaction is going to change. Mostly because the distance, inter-element distance is going to change. If you consider equilateral triangle arrangement, all antennas are at the same distance. Antenna correlation coefficient between all antennas should be almost equal. If you arrange it in a linear array, first antenna and last antenna will have largest distance. You will have lesser and lesser antenna correlation coefficient. So antenna arrangement or configuration plays a significant role in the antenna correlation coefficients. Okay. I just have half an hour, so I need to speed up. Let me skip all this thing. Okay, so let's consider separately correlated MIMO channel. Separately correlated MIMO channel is a channel model where you consider the antenna correlation coefficient into the channel model. You have introduced antenna correlation into the channel model. From there, we can find out what is the MIMO antenna performance matrix. So let's say you consider antenna array, NT antennas here, NR antennas here. So now you look at the distance between this antenna 1 and antenna 2 of the transmitter, or antenna 1 and antenna 2 of the receiver. They are not very far away, but look at the transmitter and antenna. You look at the transmitter and the receiver. Receiver and transmitter are very far away, but antenna elements at the transmitter are not very far away. Antenna elements at the receiver are not very far away. So there is a channel model where you actually separate the antenna correlation at the transmitter and receiver. You separate the antenna correlation at the transmitter and receiver and introduce that into the channel model. So ISW here is the channel model where all the antennas at the transmitter and receiver are independent. They are very sufficiently far away. There is no inter-antenna interaction. But once you have antenna interaction at the transmitter and receiver, in this channel model, receiver correlation has been post-multiply and transmitter correlation has been receiver correlation has been pre-multiplied with the channel model and transmitter correlation has been post-multiplied with the channel model. So we have introduced the transmitter side correlation and receiver side correlation into the channel model. So this model is called separately correlated MIMO channel model. That is because we have separated the transmitter side correlation and receiver side correlation and introduced that into the channel model. Why I am discussing this will be very clear here. For such kind of channel model, which is also called as Kronecker MIMO channel model, the capacity has been derived. From the capacity, we can find out what is the channel capacity loss. Channel capacity loss is one of the fundamental parameters for the MIMO antenna. So this is the capacity for the IID MIMO channel, independent channel model. There is no antenna correlation. Once you introduce transmitter side correlation and receiver side correlation, this is the ACC matrix for the transmitter and receiver. The channel capacity has additional terms here, log 2 of determinant of RRX, log 2 of determinant of RTX. So this capacity expression has been derived in this paper here, famous paper here. So this is for the IID case where you don't have any kind of antenna correlation. Once you have receiver side correlation, you have this term here, this term here, and it has been observed that this determinant is always less than 1. This determinant is always less than 1. So when you take log of them, it becomes negative. So that's why these terms are actually reducing the capacity of the MIMO channel when you have antenna correlation with transmitter and receiver, because these are negative terms. So that's how you define channel capacity loss as minus log 2 of RRX minus log 2 of RTX. This is the famous channel capacity loss people are using till today in the MIMO wireless. There's some issues here. First thing is that now some people use 10 antennas at a transmitter and 2 antennas at a receiver, and they still use this formula. But when you derive this in the wireless communication system, the fundamental assumption was that number of antennas and transmitter and receiver is equal. So you have to use it only for n by n MIMO system. You cannot use it for 10 by 2 MIMO system or 3 by 5 MIMO system. You can only use 4 by 4 MIMO system or 3 by 3 MIMO system. That's one basic major error many of the antenna researchers are doing nowadays. Okay, so that's about the channel capacity loss. We discussed about the rate gain, diversity gain, and the multiplexing gain. In line with that, I want to define the MIMO antenna performance matrix. So if you want to find the rate gain, you just find the rank of this channel matrix, and it can be found out as rank is less than a minimum of rank of RRX, rank of RTX. So these are the transmitter side and receiver side correlation matrix of the MIMO antenna. Once you have that, you find the rank of the channel of the MIMO antenna correlation matrix at the transmitter and receiver. You find a minimum of that, you get the rank of the MIMO antenna. So this will actually give you how much is the rate gain. And we also have diversity gain. So this is a probability of error for the space-time codes. You don't need to know what is the space-time code. This is the error when you send symbol C1 and you detect symbol C2. This is bounded by this. This is the probability of error. From there, you can find out the diversity gain. We have discussed that. Probability error for MIMO system is 1 by SNR to the diversity gain. Look at this term here. In the right-hand side, this is a lengthy term here. Just look at the term which is dependent on the SNR. The term dependent on SNR is this term here. And what is the power here? R tilde and R hat. That is your diversity gain. What is R tilde? R tilde is the rank of the del is RTX. Del is the difference between cohort matrix 1 and cohort matrix 2. RTX is the receiver side, transmitter side correlation matrix. And what is R head? R head is the rank of RRX. This is the transmitter's receiver side correlation matrix, antenna correlation matrix. So once you have the antenna correlation matrix, you can find out R hat and R tilde, and you can find out how much is the diversity gain of the MIMO antenna. So whatever I'm defining now is for the MIMO antenna, not for the MIMO system. We want a performance matrix for the MIMO antenna. So diversity gain is basically multiplication of rank of the RTX and rank of the RRX. RTX is the antenna correlation coefficient matrix for the transmitter, transmitting antenna, and the RRX is the antenna correlation coefficient matrix for the MIMO antenna, which is used at the receiver. Okay, so let's take some simple examples here. This is one antenna we have designed and fabricated in our lab. This is a very complicated antenna. So the basic idea is we have two dielectric resonators here, cylindrical dielectric resonator antennas, which are actually fed by the annular ring slots. And we also have a partial ground plane. So, and we made some modification in the ground plane to reduce the mutual coupling. And that is the meta grid line here. The grid line we have integrated in the ground plane actually blocks the EM wave between the antenna 1 and antenna 2, and it reduces the mutual coupling, and eventually it will reduce the envelope correlation coefficient and the antenna correlation coefficient. So we have two annular ring slot here. One is outer annular ring slot and another is inner annular ring slot. This will actually enhance the bandwidth of this dielectric resonator antenna. These are the metal parameters and the dimensions here. If you look at the electric field distribution at 5.78 gigahertz, this is the electric field distribution, and this is the typical for ICM12 delta mode field pattern, and it is defined in this Professor Guan's paper here. So we look at our antenna and 5.8 gigahertz, and it gives us the field pattern for ICM12 delta mode. And we look at the scattering parameter, we observe that it has a bandwidth, has a very good bandwidth, and mutual coupling. Bandwidth is from 5.7 to 6.25 gigahertz, and mutual coupling is less than minus 15 dB. One thing is that I have reviewed many papers. Many people just write S11, S21, S11, S21 here. So scattering parameter has amplitude and phase. What we are plotting here is only amplitude, so we need to put modulus sign here. Okay, so we put different number of grids here. 754 gives us the best impedance matching, so we have gone for that. And this is the evolution of the antenna ground plane. First is the uniform ground plane, which is the usual antenna ground plane. Then we remove some partial ground plane. Then we put the meta grids line here. Then because of that, mutual coupling has been significantly reduced. It can be observed here. Mutual coupling is very good, much lower than minus 15 dB. This is the fabricated antenna. This is the prototype. We have DRA here, and this is ground plane. This is the meta grid line. This is a partial ground plane. And this is the measured scattering parameter and simulated scattering parameters. This is the radiation pattern. And another thing is that one point to be noted here is when you plot the radiation pattern has both E plane and S plane. It also has a copolar and cross polar. So for the copolarization and cross polarization, copolar components should be very low, and many people just plot the copolar one. You need to plot the cross polar one also, so that we know how much field is going for the cross polar component. And this again here, we can see that gain and the ECC for this antenna is very good, so less than 0.046 within the bandwidth of the antenna. Gain is also okay, 4.18 to 5.3 dBi. It's much better than the microsтрip antenna. Usually microsтрip antenna will have 1 to 2 dBi, but here it is 4 to 5 dBi. DRA usually have a higher gain. So this is a comparison table here. We can see that our antenna is having antenna size, antenna volume is 0.407. This is very much lesser than the reported antennas in the literature. And another thing is that inter-antenna element spacing, IES, inter-element spacing is very less. We started our research with the traditional antenna has inter-element spacing of λ/2. So with my PhD scholar, we actually try to minimize this inter-element spacing, and we have gone up to 0.091 λh. Λh is calculated at the lowest frequency, so that is the maximum dimension you can have. And our idea is to minimize the inter-element spacing so that we'll have more and more compact antenna array. And in the process also, we don't want to compromise with the MIMO antenna performance. And in order to find out the MIMO antenna performance, we need to know what is the SEC. SEC can be calculated from the 3D radiation pattern calculation of the ECC. ECC I have shown you is less than 0.46. So SEC is less than 0.214. Inter-element spacing is 0.091 λh. And from there, you can find out the transmitter side correlation. See, once you have SEC, you can fill up the matrix. We assume a 2x2 MIMO system employing the same antenna. So this is the transmitter side correlation matrix and receiver side correlation matrix. We can find out how much is the diversity gain of this MIMO antenna. Not for the MIMO system, this is for the MIMO antenna. This is our own proposal, our own work. Diversity gain is 4 and rank is 2 and channel capacity loss is 0.1727 bits per hertz, bits per second per hertz. So channel capacity loss is not much. So this is a good performance criteria. We are getting the maximum diversity gain, maximum rate gain, and we are having minimum channel capacity loss. So this is another example. So here you can see that we have used neutralization line here. This is slots. This 2 slots gives us 2 bands. This is a dual band, dual port MIMO antenna. So because of this employing the neutralization line, even if we have an inter-element spacing of very less, and I will show that later on, we have still very good mutual coupling. Mutual coupling is still less than -15 dB. Because of the employment of the neutralization line. And this antenna can be used for many applications here, listed here. We look at the ECC. ECC is less than 0.6211. So ECC is very less. Acceptable value is 0.5, but we are having 0.06. Gain is also considerably good, 3.66 dBi. And so the basic idea is the performance of this MIMO antenna should not be compromised when we make it more and more compact. So as I have told you, inter-element spacing is very less here, 0.092 lambda x. Traditionally is lambda by 2, ours is 0.0292 lambda. So it's a very compact MIMO antenna array. You can fill up the coefficient, antenna correlation coefficient from the ACC calculation, and you can find out the rank and find out how much is diversity gain. We are getting maximum diversity gain, maximum rank here. Channel capacity loss is also very less, 0.185 bits per second per hertz. It's another antenna we have designed. We have 4 dielectric blocks here, so they are very closely packed. The inter-element distancing will be less than 0.1 lambda. So how do we overcome the interaction between this? We tried different techniques here. Feeding techniques, another is we put a cross metallic walls here to reduce the inter-antenna interaction. So dielectric resonator antennas, this is the fundamental equations where you can decide the dimensions of these dielectric blocks. And one point is that gain of this antenna is 4.0 dBi. So all the gains are always measured in dBi. I have come across many people use gain as dB. That's not correct because we are having gain with respect to that of the isotropic antenna, dB over isotropic. So the idea is the fit lines for the adjacent antennas are in perpendicular planes. So this is a fit line here. This is a T-shaped microstrip fit line. We have a slot here. We have broadened this slot so that signal can be coupled properly from this microstrip fit line, T-shaped microstrip fit line. And they are perpendicular. Adjacent fit lines are perpendicular so that they will excite orthogonal modes. Okay. Let's look at the radiation patterns. Looking at the radiation patterns, you can see that, see, this is X, this is Z. So we have, this is TEY1 delta 1 mode. Because of the similar excitation for DB1 and DB3, DB3 will also have similar kind of field pattern. DB2 and DB4 has similar kind of excitation pattern. This is Y-axis, this Z-axis, this X-axis. This is TEX delta 1 mode. Okay, so the idea of using the vertical metallic plates, look at this. These are the radiation pattern, 3D radiation pattern for DB1, DB3, DB2, DB4. You look at this here. These are red color here. This is, you have a high radiation here. There's a lot of inter-antenna interaction. But let's say when you apply the vertical metallic plates to block the electric field radiation from one antenna to another antenna, you can see that this has become yellow. Field has been reduced. So that's how you reduce the mutual coupling. And this is the scattering parameter versus frequency, and you can see that this this is without the metallic plates. If you don't use the metallic plates, then the mutual coupling is higher. If you use the metallic plates, mutual coupling is lower. One point to be noted is return loss is always positive for the antennas. S11 for the S12 for the antenna is always less than 1. So when you take log of that, it will be a negative number. But for the return loss and insertion loss, you are multiplying minus 20 log of. So it becomes always positive, insertion loss and return loss. I have seen many people plot return loss and insertion loss, and they have a negative value here. Okay, so when we put the metallic plates, you can see that bandwidth is 5.45 to 6.5 GHz, and mutual coupling has been reduced below minus 20 dB. That's a very good mutual coupling. This is a performance comparison, and you can see that our antenna is having a very good bandwidth, and size is smallest here. Size. And mutual coupling is less than minus 20 dB. Size, you look at the size, ours is smallest because of the closely packed MIMO antenna elements. And we don't want to compromise the antenna performance. We calculate the diversity gain and rate gain. It's giving the maximum diversity gain and rate gain. And channel capacity loss is also very less, 0.0704 bits per second per channel hertz. That is because ECC is very low for this antenna, 0.0044. So SEC will also be very small. You look at the inter-element spacing, it's 0.081 lambda h. This is a 6-port, 6-element MIMO antenna array. Okay, so let's look at it. So here also, there are two cases. This is a neutralization line, without neutralization line and with neutralization line. You don't have any neutralization line here. This is a current distribution. When you put the neutralization line, currents actually oppose and minimize the mutual coupling. That's the basic idea of using neutralization line. It will minimize the mutual coupling. This is a simulated gain and efficiency. And this is the ECC versus frequency for the MIMO antenna. ECC is less than 0.5. As parameters, we find out that bandwidth is from 3.44 to 4.68 GHz. Mutual coupling is less than minus 15 dB. This is the acceptable value of the mutual coupling. This is a radiation pattern. You have to show the copolar and cross-polar component. This is a performance comparison. What we see is that our antenna has a very small volume and inter-element spacing also is smallest. And we find out the MIMO antenna performance matrix. We look at the inter-element spacing is 0.076 lambda h. Traditional is 0.5 lambda, or is much lesser. And diversity gain, it gives you maximum diversity gain and rate gain. Channel capacity loss is very high here, 5.3341, because you see that ECC at the lower frequency was very high. So we cannot find a real solution to this. Okay, I think I will skip this. Okay, so what is this multi-user MIMO? In the multi-user MIMO, we'll have many users. User 1, user 2, user 3. That's the usual scenario you have for the cellular communication. So in this, you have uplink and downlink. Uplink is when your mobile is sending signal to the transmitter base station, and the downlink is when your base station is sending signal to the mobile user. So there will be two kinds of gain, two kinds of capacity, one for uplink and one for the downlink. So the performance criteria for the multi-user MIMO and the single-user MIMO would be different because we have uplink and downlink. So now, let us try to characterize the performance for the MIMO antenna in the multi-user scenario. So this is the multi-user scenario. You have many users here, and we're considering the uplink scenario. And how many antennas every users are employing? Many antennas is using. And at the base station also is employing many antennas. At the mobile user also many antennas. We're considering the uplink scenario. So we can find out the channel capacity loss for this. And this, I have derived the channel capacity loss for this. Using this formula, you can find out the channel capacity loss. You can look at this channel capacity loss. This for only for the uplink. We have not done for the downlink. Downlink has a power allocation problem. Uplink do not have power allocation problem. So this capacity, channel capacity loss expression is much different from that of the single user system. So you cannot use this channel capacity loss of the single user system for the MIMO antenna which is used in the multi-user scenario. So we have calculated the channel capacity loss using these cases for different cases, and channel capacity loss for this MIMO antenna we have used for a single user system. And we see that channel capacity is 0.00001, which is much lesser than what we have for a single user. That's one of the major advantages of multi-user MIMO system. We can minimize the channel capacity loss. Another example, this recent paper And this is a smartphone which employs 4 antennas. These are L-shaped resonators, 4 L-shaped resonators. These are the mutual coupling reduction techniques. This is a very recent paper published somewhere in 21 April. We have found out the channel capacity loss in the multi-user setting, and turns out to be 0.0014. And another case also we have considered. This is also a very recent paper. Here in the smartphone, they are employing 8 antennas. 8 antennas. It's a closely packed MIMO antenna array, and they have achieved very good mutual coupling also. I actually found out what is the channel capacity loss for the antenna they have designed from the envelope correlation coefficient they have reported, and it's very low, 0.00050. It's a very good antenna design. So we can understand what is the performance of the MIMO antenna in the actual MIMO system by using this kind of analysis. Okay. So let us discuss a little bit about the evolution of the MIMO system. So we have gone from the single user system to multi-user system. We have seen that channel capacity loss was minimized. So now the idea of the massive MIMO is that, let's say you have a terminal here with K antennas. Let's say there is a multi-user scenario where you have K users. So look at the antenna 1 and antenna 2 of the terminal. The inter-element spacing is very less. But mobile user 1, mobile user 2, mobile user K, there is a lot of distance between one mobile user to another mobile user. It's much larger than the distance you have at the terminal where antenna 1 and 2 are placed. So why don't you distribute this antenna? Okay, this animation is not working. If you distribute this antenna 1 to mobile user 1, antenna 2 to mobile user 2, antenna K to mobile user K, then inter-element spacing has been significantly improved. Because of that, you'll have diverse path for the signal to go. So you'll increase the diversity gain. So that was the one basic idea of going from multi-user MIMO to the massive MIMO. And another thing is that, what is the basic idea of going from massive MIMO to cell-free massive MIMO? That I will briefly discuss here. So the one of the major problem with the cellular communication is that if you consider a user at the cell S, so these are the cellular cells, hexagonal cells. This is a base station serving one cell, another base station serving another cell. We have considered around 5 of them. So every base station is serving every users in one cell. But let's say I am considering a user of this cell 1. Home cell is cell 1, but it is located at the base of the cell, at the boundary of the cell. So now this user will pick up signal from base station of second cell, base station of third cell, base station of fourth cell, base station of fifth cell. So what is the problem with that? So if you calculate the capacity of this user at the cell S or cell boundary, capacity is log to 1 plus SIN. We have calculated capacity as log to 1 plus SNR, but when you have interference, then it has to change to SINR, signal to interference noise ratio. So how do you calculate SINR for this user at the cell S? The power desired divided by the power noise, power inter-user interference, inter-cell interference. So now this is picking signal from all the nearby cells, so inter-cell interference is going to increase. This power is going to increase. So if this power increase, SINR decrease, capacity will decrease. So this is the inherent problem in the cellular communication. This is called near-far problem. Very near to the interfering cells, but very far away from the desired cell. It is not solvable, and it is existing in all kind of cellular communications. So in the cell-free massive MIMO, what we suggest is free the concept of cells. There is nothing like cells. This is a very recent technology which is proposed for 6G communication. Massive MIMO was already used for the 5G communication. Cell-free massive MIMO is proposed for the 6G communication, beyond 5G communication. So here, the idea is that, what is the best situation for the user? Let's say you consider user 1, if it is surrounded by many access points, it can communicate to any nearby access point. That's the best situation for the user. It will be always surrounded by the users. And it will have the best performance. So the idea is, let's say if base station is having many antennas, why don't you distribute every antennas of the base station? This animation is not working here. So if I distribute this antenna 1 to access point 1, antenna 2, access point 2, antenna 3 to access point 1, all the access points are very far away. So first thing, when you consider from the multi-user MIMO to the massive MIMO, you have distributed antennas from the multi-user MIMO, the base station at the terminal to the every user. So here we are actually distributing the antennas of the base station to access point. So all the antennas will be very far away. We'll have macro diversity. So we'll have macro diversity at the user side as well as at the base station side. It will have very good performance. So that's why people are going for cell-free massive MIMO for the 6G communication system. This is the channel model. I think I do not have much time, so I will briefly discuss it. Let's say this is a scattering model for the user. No? So we have a user, this is the base station. Base station is at a very high height. User is at a lower height. So now user will be always surrounded by scatterers. So if you assume that user is surrounded by ring of scatterers and signal which is going from the user is confined within this angular standard deviation, and this center angle is the nominal angle. All the signals are confined within this. User is surrounded by ring of scatterer. All the signals which are going from the user is confined within this. From there, we can come up with a channel model for the local scattering. And using that, we can find out the capacity for uplink some rate and downlink some rate for the cell-free massive MIMO and massive MIMO and compare the two. When we have correlation at the user side. So you can see that this red curve is the uncorrelated case. Blue curve is always the correlated case. You can see that in all cases, red curve is higher than the blue curve. This is for the uncorrelated case. That means you don't have any kind of correlation. And you can also see that another thing is that cell-free massive MIMO, cell-free massive MIMO is the upper curves here. These curves here are for the cell-free massive MIMO, lower curves are for the massive MIMO. You can see that capacity for uplink and downlink for cell-free massive MIMO is much larger than that of the massive MIMO. That's why people are going for cell-free massive MIMO in the 6G communication. Okay, so I will try to come to the summary of the talk. So we have discussed about the different types of MIMO, single user MIMO, multi-user MIMO, so and cell-free massive MIMO and massive MIMO. And we have defined the antenna performance metrics for the point-to-point MIMO system as well as for the multi-user MIMO system. And performance metrics would be in line with the MIMO system performance, diversity gain, multiplexing gain, and channel capacity loss. I have observed that channel capacity loss expression, which is available in the literature people are using, that is only for single user MIMO, and when the number of transmitting antennas and number of receiving antennas are equal. It cannot be used for the multi-user case or when the number of transmitting antennas and receiving antennas are different. We have also derived what is the diversity gain and multiplexing gain for the MIMO antenna. It was in terms of the antenna correlation coefficient matrix. So antenna correlation coefficient matrix is a very important parameter. Once you have that, you find the rank of that, multiply the rank of the antenna correlation coefficient matrix at the transmitter and receiver, you get the diversity gain. And when you find the minimum of the rank of the transmitter side correlation and receiver side correlation, you get the multiplexing gain. Okay, and we have also discussed about the effect of special correlation on massive MIMO and cell-free massive MIMO. We have also discussed briefly about special modulation where only one antenna is active, which will completely remove the inter-antenna interference. And these are the references. Thank you. I still have time for questions. Okay. Please feel free to ask questions.
Excuse me, sir.
Yes.
Sir, I don't have a background in this topic, but I have a query. When we do this spatial spatial modulation,
Yes.
will it affect this rate error you are explaining?
Okay. So we have done a lot of research in spatial modulation.
Yes.
What we have and other researchers claim is that spatial modulation is actually giving the same diversity gain with that of the full flex MIMO system where you use all the antennas. It is giving the same diversity gain. That means it is giving the same error rate with that of the. So we are not compromising anything on the error rate. there's a little bit compromise in the uh, spectral efficiency. But we have other techniques, advanced spatial modulation techniques, which will improve the spectral efficiency. Data rate we are transmitting will be a little bit reduced because we are just exciting only one antenna. But
So
if we excite,
those spectral techniques are related to coding, channel coding, or other things.
this is not actually coding, but this is a wireless technique actually.
Okay.
Modulation techniques. You have modulation.
Okay, modulation. Okay.
We are doing modulation over the space. Antenna is giving some chance for us to do modulation over the space. It's a new modulation, so that's why spatial modulation over space.
Okay, sir.
I think I have answered the question. Any other
Ji, ji,
question?
ji. Thank you, sir.
You are
Yes, sir.
welcome.
One question from Mr. Sachin Yadav. Please
Okay.
explain dBi and dB gain for
Okay.
reference antenna during DUT.
Yeah. That's a very good question. See, DBI and DB are very different things. See, antenna is a passive device. First thing is that antenna is the passive device. Antenna is no longer an active device. How could antenna has a gain? So antenna has a gain, right? We always discover about the antenna gain all the time. Antenna gain is one of the most fundamental parameters. But this gain is not the gain we have in amplifier. Antenna is a passive device. So this gain is with respect to that of the isotropic antenna, which is it's not a practical antenna, it's a hypothetical antenna which radiates equally in all directions. So now if your antenna is radiating beams which are having more power in one direction, you will have a gain in that direction. So gain over that of the isotropic antenna. So this is a very fundamental question. So dBi is a dB over isotropic. The reference antenna you are comparing for the gain is the isotropic antenna which is radiating equally in all directions. I hope I answered the question. Any other questions?
Yes, thank you, sir.
Welcome.
Okay, sir. Thank you very much. Thank you, Dr. Rakhesh Singh Kshetrimayum, sir, for the elaborative and insightful talk on inter-antenna and its effects in Mimo Wireless. Sir, thank you very much for this session.
Thank you very much, Dr. Aditya and Dr. Pankaj, for giving me this opportunity. It was very good to have interaction with you all guys.
Yeah,
Thank you
same
very
here.
much.
Thank you, Professor Rakhesh. Thank you very much for be a part of this Untitled FDP, and in near future also we will contribute.
Yeah, definitely. Thank you very much.
Thank you, sir. Thank you very much. Thank you very much.
Okay. I'm
Thank you.
disconnecting.
Okay, sir. Now you can leave, sir. Thank you.
Okay, dear participants, thank you very much. The session is over for today. Thank you. Thank you.
So tomorrow is the last day. So we will connect. Two more sessions is there in tomorrow's day. So afterwards we will conduct a test. Okay. So all the instructions we will provide you in the tomorrow morning. Thank you.